Yeah, hi everyone. Thanks for coming to this talk, DirectX State of the Union Raytracing and PIX Workflows. My name is Claire Andrews. I'm a dev lead for D3D. I've been on DirectX team 15 years. I'm here to present the latest of what we've been working on and then work with Adam to talk about PIX tooling. Yeah, quick reminder to, if you can, silence your cell phones. And then we'll be having the talk here. If you have questions after, we'll be in the alcove. If you take a left and another left, there's some windows, we'll be over there if you have any questions at the end. Yep. So we'll start here. Yeah, so today we're going to dive into the future of DirectX with a packed agenda of innovations and announcements. First, I'll recap last year's DirectX announcements at GDC with our plan for enablement of neural rendering. Then we have some exciting announcements with new features in our upcoming release of DirectX Raytracing, or DXR 1.2. Besides DXR 1.2, I'll share with you some AgilitySDK features that you can use right now. You might remember AgilitySDK is our redistributable DirectX, so that you don't have to wait for a Windows OS update to take advantage of our new features. Finally, Adam has some exciting announcements for PIX, including custom mesh, custom texture visualization, PIX events, and more. So stay tuned for that. All right. So let's start with a recap of DirectX at GDC 2024 last year. Last year, we announced DirectSR, which lets you use GPU-accelerated upscaling in a platform-agnostic way. We announced that with work graphs, it's a new step in giving you flexibility around what executes on the GPU. Just to recap that, if you think about GPU workloads, like not just what they are, but how you execute them. Traditionally, well, how does that work? You call some C++ APIs, you populate a command list, execute the command list, that's fine. Or you can call execute indirect, populate your argument buffer on the GPU, instead of the CPU. You can do some limited things that way. Fast forward to now, the recent new feature we've announced is work graphs. So this is full flexibility of scheduling from the GPU. It affects how you generate GPU commands. We designed work graphs to be a good fit for workloads like Unreal Engine 5's Nanite. With Nanite, you can have algorithms where the size and the type of the GPU workload you're executing is dynamically determined. It's not statically determined. So it can make more sense to schedule those workloads from the GPU. We built work graphs for scenarios like Nanite that can benefit from this more flexible GPU-side programming model in terms of how commands get dispatched. I'll point out in the initial release of work graphs, the leaf nodes of the graph, what were they? They were compute workloads. Well, since then, we've announced a preview of work graphs mesh nodes. So from there, a leaf node of a work graph can kick off a graphics pipeline through a mesh shader. So I'm excited to have Max here from AMD to showcase a demo using these features.
All right, thank you, Claire. So you might remember our demo from last year, where we took some pre-made assets, throw them into a work graph, and then we procedurally assembled them into a nice marketplace and other things. And thanks to mesh nodes, we were able to render these assets directly from inside the work graph. And this also netted us quite a sizable performance improvement. But this hardly is everything that mesh nodes are capable of. So we were asking ourselves, can we do more? Can we procedurally generate more things with work graphs and mesh nodes? Maybe even all the things. That's exactly what we did for our first mesh node sample that we co-released with the mesh node preview, where we have different biomes and a fully procedurally generated world with like trees, grass, there are even some butterflies and bees flying around in there. And you can find this sample over on gpopen.com. Now, there are a few issues with this sample. One is that now there's everything procedurally generated. There is sort of no artist control anymore. So you're completely relying on the algorithm that you coded to sort of generate the world that you want. And the second thing is that, well, we had some trees in there, and while they're quite nice and stylized and fit the art style of the demo, they're not really match the real-world counterparts that well. So together with our friends at Coburg University, we sort of set out on a quest to generate more realistic trees with work graphs, since we thought this might be a nice use case to show off the capabilities of mesh nodes. So we first need to sort of take a quick look at a real-world tree. We can see that trees start out with a tree trunk, and there are some branches growing out from them. And if you even take a closer look at this tree, you can see that there is even some recursion going on in there with branches growing out of branches. And well, it was still winter time when we made these slides. You can imagine that a tree would also have leaves in the summer. So now the question is, how do we draw all of these things? Well, in theory, for all of these things with the tree trunk, it can have many, many branches. All the branches can generate even more branches. So there's quite a lot of amplification in there. So if we put some numbers in that and sort of add all of these up, we'll end up with like a worst case estimate of around 40 gigabytes that one tree could take up. So obviously that wouldn't really work. We can't really store 40 gigabytes away for a tree or reserve that memory. And we don't really want to just render one tree, we want to render many trees. So here comes a savior, and it's called mesh nodes. Because now we can directly sort of render the tree from inside the work graph. So we don't have to care about storing away all of these, all of the data that we need for drawing. And this allowed us to scale up the trees to over 1,000 trees in our demo scene here. So as we take a nice fly-through for Opac, let me quickly talk about what we did here. So we have this scene with like every tree here is fully procedurally generated every frame. So there's nothing cached, nothing sort of stored away in between frames. Everything starts from scratch. And for the entire scene, we're sort of generating between 20 and 40 million triangles just for the procedural vegetation alone. And you can see some nice example of this. For example, we have our hedge maze here. This one has like over 400 trees condensed in a very small area. And it's still running just fine, even on like medium tier hardware. Now, with this being sort of procedurally generated every frame, this allows for some nice features like artist control, because we can sort of procedurally adjust the parameters of the tree. For example, we can weigh it down with more fruits and see the updates in real time. We can even make a tree a bit more happy or a bit more sad. Let's just leave it at happy tree. And then once we're happy with all the parameters, we can pick from one of virtually infinite amount of trees just by changing the random seed used for generation. Now, if that's not enough, we can even take one step further and sort of add a control point to each tree, where you say, okay, we want the tree growing in this direction. Then we can move that one around and adjust how the tree is growing. And also one thing, if everything is procedurally generated every frame, we can sort of add some global parameters as well. For example, we can adjust the season of the sort of entire scene. So you can now see all the leaves turning nicely yellow or fiery red. You can see all the fruits disappearing. Now all the leaves are gone and we're heading into winter time. For example, all the snow here is also procedurally generated within the work graph. And as we sort of head back into springtime, you can see that all the leaves grow back and all the blossom is also growing on the trees. As we sort of head back into summer, you can see all the fruits growing back on the apple tree, and we're sort of right back where we started. Now, final word on level of detail. In most games, you'd have some static LODs, and you'd either have to deal with the LOD pop, or you'd have some fading in between those. But as we sort of generate everything on the fly in the inside the work graph, we can have sort of a seamless LOD fade and just scale back the triangle count however we see fit for the distance on the camera. So we have a tree scaling back from roughly 3.5 million triangles to just shy of like 9,000 or 8,000 triangles, depending on the distance of the camera. And as the camera moves back in, we can see all of those triangles generating back in. So hopefully you've seen a glimpse of what mesh nodes are really capable of, and we hope that you try them out and have some fun of your own. With that, I'll hand it back to Claire for some more DirectX updates.
Yeah, thanks, Max. It's really exciting to see what work graphs are capable of, especially with mesh nodes, so ability to fire off a graphics pipeline from a work graph. So we talked about work graphs. I also want to recap something from last year that we announced in our roadmap. We wanted to talk about exposure of neural rendering primitives last year, so I'll talk about that here too. In graphics rendering, we have sometimes some visual or lighting computation that has some common paths like BRDF, something computationally intensive. It turns out a lot of these computations can be pretty well fitted by polynomial. Turns out GPUs are really good at doing operations on those. So there's today in the ecosystem dedicated silicon to take advantage of that principle. So with that, I wanted to share with you that our roadmap includes a future plan to let Windows applications take advantage of that hardware acceleration. Neural rendering we see is in part controlled at the shading language level. With DirectX, we're imagining that typically being HLSL through new features in Shader Model 6.9. Neural rendering has a lot of interesting applications. There's radiant fields, lit materials, texture compression. We see DirectX as being perfectly suited to be a pathway into enabling neural rendering across GPU platforms. And then cooperative vectors is our first step into that. If you want to learn more, you can watch the recording of Sean Hargrave's Advanced Graphics Summit talk from Monday. It's called Cooperative Vectors and Neural Rendering, and then there's a link to it right there. So next, we're excited to announce today a new version of DirectX Raytracing, DXR 1.2. And then I'll be handing it off later to Mika from Remedy to show what you can expect with this. Pretty exciting. So upgrading to DXR 1.2 unlocks unparalleled performance gains with improvements reaching 40%, sometimes in complex scenes, like those in our demo with our partner here from Remedy. You can experience smoother frame rates and richer ray trace visuals with greater efficiency, pushing the boundaries of real-time ray traced rendering. So you want to look forward to that and then experience faster ray tracing with our DXR 1.2 preview that we're going to have ready for you in April 2025, so in about a month. First, I'm just going to provide some background on ray tracing just in general in case you're not familiar with it. So this is a screenshot of the Remedy game Control without it, and this is with ray tracing enabled. So you can see some differences here. This is with before and after. You can see the reflective details on the windows, for example. We have this challenge in computer graphics of figuring out how light interacts with objects so that we can create realistic shadows and reflections and other lighting effects. Instead of a crude approximation of light, we can use ray tracing, which mimics real-world optics. The technique's not new, right? It's been around since the 80s. What's new is that it's real-time. And as you know, we've made it available for you in DirectX. So even though it is real-time nowadays, it's computationally expensive, and we're early on the path to mainstream adoption. With that, I wanted to share with you our roadmap to continue enriching DirectX ray tracing and to keep moving the ray tracing pipeline forward, and a couple features that we're announcing right now that you'll be able to use in AgilitySDK release very soon, coming up in late April, so about a month. I want to share with you Microsoft is adopting hardware industry-aligned ray tracing features that offer significant performance improvements across platforms. So first one, Opacity micromaps are a new ray tracing feature we're announcing right now in DXR 1.2. They're a performance feature proven to make ray tracing faster, up to 2.3x in path trace titles, and to do that by removing the need for some any hit shader invocations entirely, or reducing the number of shader invocations without any loss in quality. Like, consider how you think about alpha testing. Usually, high detail opacity information gets conveyed through alpha textures. Well, for ray tracing, that can be really costly to evaluate in shaders. What if we could take advantage of dedicated hardware that can use alpha information that's stored in a way that's more efficient to retrieve during ray tracing traversal? Use a format that exploits locality in opacity data, and then apply that to effectively alpha test out some shader invocations of a geometry, or sometimes the entire geometry. This is made possible through opacity micromaps. There's hardware in the ecosystem today to accelerate opacity micromaps, and so it's part of this DirectX announcement here to make that capability available to you through DXR. I'll share with you a sense of what it looks like in the DirectX API. This is not going to be a full spec. First, there's the offline build step. So you could, for example, use NVIDIA's Opacity Micromap SDK for that. Then you build an OMM array. The OMM array gets used when you construct your bottom level acceleration structure, or BLAS for short. And then the bottom level plus a top level acceleration structure gets used to create the full acceleration structure, or AS for short. Another piece of the API surface for building the OMM array, there's a new acceleration structure type that you use with the API build ray tracing acceleration structure. This produces your OMM array. And from there, there's a new geometry type that you use when constructing your BLAS. It's called OMM triangles. OMM triangles is a new type of ray tracing geometry primitive. It's got its own desk structure, like you see here. The desk structure takes the inputs of triangles and linkage information, and then construction of the BLAS will include the micromap. So from there, yeah, you bind your acceleration structure the usual way, call traceray against it, and that's it. You enjoy the benefit of alpha tested work just being skipped. Yeah, so for moving your game onto this feature, it's pretty straightforward. Your traceray calls will have the benefit of this up to 2.3x figure that we're sharing on that. It's super exciting. So that's the first part of DXR 1.2. The other part I'll also run through right now. So the other feature we're happy to announce today in DXR 1.2 is SER. It's shader execution reordering. SER is a performance optimization that's all about execution coherency. It can improve ray tracing performance up to 2x in path trace titles. When we think of running a ray tracing shader on the GPU, how does that work? You've got many threads executing in parallel. Well, there's execution divergence, right? Like when different threads execute different shaders or take different branches in a shader. And there's also data divergence. So you've got different threads accessing different things in memory in patterns that are expensive to cache. So I'm happy to share that SER actually improves both of these. It does this by letting the application tell the driver how to reorder threads in a way that improves coherence of execution. Like if you see this diagram, you've got some rays traced from the viewer to these disparate points in a scene. Since all the rays are hitting different locations, there's not much rhyme or reason behind which rays are grouped together. With SER, the rays that have similar shading get grouped together. So with more coherence, you have more efficiency. For the main part of how you adopt SER, it's pretty simple. It's this HLSL intrinsic called maybe reorder thread that's available to your raygen shaders, or ray generation shaders. The name maybe reorder thread reflects the fact that the usage is just super simple. You can write your shaders once in one platform agnostic way, irrespective of whether the underlying implementation actually does execution reordering. So that's it. You adapt your calling of traceray to include calling the maybe reorder thread intrinsic, and you pass it a data type that stores the result of traversal, intersection testing, any hit shading, depending on your situation. And that's it. When you do that, you enjoy closest hit shading and misshading that gets executed in a more coherent context. If you want to find more details on this, you can look at our spec documents, maybe reorder thread. It's in our public HLSL language spec in this GitHub repository with a link here. Yeah. So talked about this HLSL intrinsic. So with a proven performance benefit of up to 2x in path trace titles, we view this as a powerful benefit that requires no change to any of your assets, no change to how your pipeline's configured, just a relatively small change to your raygen shader in some cases, and you can reduce divergence in execution really significantly. I also want to call out the fact that new versions of DXR are incremental, meaning each version of the new feature includes the features of the previous version. So on platforms that support DXR 1.2, you can find all the functionality we've called out, plus trace ray inline and all the other ray tracing features that you'd expect. That's it. So from here, I'll hand it over to Mika for a really cool demo for Remedy. Thank you.
All right. Hi, everyone. So I will be running through some of the performance benefits that we can see in Alan Wake 2 using these techniques mentioned just now by Claire. Large parts of Alan Wake 2 are located in this dense primordial forest in Pacific Northwest. And we rewrote our Northlight geometry rasterization and skinning pipelines to be able to cater for the necessary level of detail this world needs. The vegetation is modeled as high-density skinned geometry, which uses alpha testing. And in this location, we rasterize 5 million directly visible triangles and a bit over 9 million for shadows. And as explained earlier, the opacity micromaps can be used to reduce the amount of alpha test shader invocations. And when turning off alpha testing geometry in this location, you can see that most of the screen is in fact covered by vegetation that can benefit from accelerating opacity rendering. In Alawake 2, we expose a fair number of ray tracing settings for the user to choose from. And in a demo build where we switched to using DirectX API for these techniques, we're using something called ray tracing high setting. And in this high setting, we replace some of the key algorithms with better ray tracing alternatives and to better demonstrate and highlight the benefits of these techniques. So for rasterized shadow maps, they are replaced by reservoir sampling-based ray tracing when figuring out visibility of direct light contribution. And instead of using screen and SDF ray marching-based reflections, we do trace indirect light path up to 3 bounces. And for reflections on transparent surfaces, we use ray tracing to figure out exact hit location with geometry. On native 1440p resolution, we shoot around 37 million rays per frame on this ray tracing preset. And on 4090 GPU, the cost of all these ray tracing effects would be 16.8 milliseconds. And using both shader execution reordering and opacity micromaps, we can cut this down by 1/3. So in this case, down to 10.2 milliseconds. We observe similar benefits in other locations as well. Using shader execution reordering or opacity micromaps alone, both give already measurable performance boost, but combined, they quite consistently drop, in our case, the cost by 1/3. We are happy to switch now using DirectX API for this because it reduces the special code paths in our engine, and it also allows in the future a larger audience to be able to enjoy the benefits of these optimizations. Thank you, and back to you, Claire.
Thanks, Mika. This is really exciting. I'm happy to share that we're partnering with AMD, Intel, NVIDIA, and Qualcomm to bring you hardware support for DXR 1.2. So stay tuned for the release of DXR 1.2 in April. It's coming up pretty soon. And then keep an eye on the DirectX developer blog. There's a URL, aka.ms/DirectX, for the release announcement. All right, so in addition to new ray tracing improvements, I also wanted to share with you some AgilitySDK features that we've released in the past year or so. These are all pipeline agnostic, so you can take advantage of them from ray tracing or the raster pipeline, either one. So first up, 9995 RTV and UAV is a texture format that's popular for HDR since it has a shared exponent. That format is 9995. Some advantages of this format: it's more efficient to store than FP16, but it also has higher dynamic range than FP16. The trade-off is it doesn't have a sine bit or an alpha channel. Well, if your scenario doesn't need that, then you don't care. So anyway, we've had this format for a while, but you couldn't make it RTV or UAV until now. So we've announced support for that. Next, I'll share with you some memory usage improvements we've made available for you. So you know how in D3D you create resources to share with the GPU. These take up some amount of memory. The exact amount depends on the type of resource, and we have different choices for that. We have different choices for like the backing store of the resource and different policies. One category of policy is place resources. There's this kind of in-between option that gives you some flexibility in terms of the resource allocation, but you don't have to micromanage a ton. As for how much memory your place resource takes up, sometimes you're at the mercy of alignment. Before this feature was introduced, the place resource alignment maybe you already know what it is. It was 64K across the board. That's a lot. The reason for that was the alignment used to be kind of indiscriminately based around worst case scenarios that existed when D312 was introduced. So time passed. Now we know of cases, and it's actually pretty much all cases, where the GPU implementation can actually do better. So this feature unlocks that ability, and you can spend memory only for what you actually need. So thanks to this feature, place resource alignment, I can share with you, it's improved from 64K all the way down to as low as 8 bytes in some cases. And then committed resource alignment is also improved too. Final thing, our HLSL future. So I'll share an announcement we made about our future HLSL compiler. So back in September, we announced some plans in our future roadmap. So as you know, like when you write shaders that you use with D3D, typically you compile them with DXC compiler to a bytecode format, and typically that's DXL, DXIL. So first thing I'll say is that today, that compiler, this HLSL compiler, is based on a really outdated fork of LLVM. So for a compiler, it makes it hard to benefit from the changes and improvements that are happening in LLVM main and to upstream our changes to the LLVM code base. So with that, I wanted to share our plan to modernize our HLSL compiler and get it onto LLVM main. Once we do that, we can get the benefits of a bunch of agility and then make it faster and easier to develop new compiler features. Second thing is the bytecode format. So D312 today accepts 2 shader bytecode formats, DXPC and DXL. DXL we introduced made sense at the time. Time passed, and then the shader compiler development process over time became less closed and more open. So from that perspective, moving to an open bytecode format just made sense. SPIR-V, we believe, offers some advantages. It compresses well, it's open and community-driven, and it's said to be easier to parse than DXL, and it has a unified spec. So with that, last September, we announced our plan to introduce a new shader model with a new compiler version. That shader model will be based on SPIR-V, and DirectX will accept SPIR-V. So I want to assure you we have a commitment to backwards compatibility. We'll have paths that let you use either DXL or DXPC like you have today, plus SPIR-V in the future. So this is going to be a long process, and it's still pretty early, but I wanted to recap this roadmap item for you and let you know there's a lot to look forward to. And then you can head to our blog for more details on that. All right, so that covers DXR 1.2, which is coming to you in a preview in April, pretty soon, and a couple other new features and our SPIR-V plans for the future. So from here, I'll hand it to Adam to talk about PIX.
Thank you, Claire. So my name is Adam Miles. I work in the Xbox Advanced Technology Group. This part of the presentation was originally due to be given by Austin Kinross, the dev PIX lead, but due to extenuating circumstances, I've had to step in his place. Rest assured, though, I've worked closely with the PIX team on an almost daily basis, and I'm probably one of its most avid customers, so I should be able to speak well to everything that Austin would have delivered here today and also take your questions after the presentation. So when we say DirectX, what do we mean? Obviously, the most prominent part of DirectX is the D3D API, but there are other pieces to the puzzle that Microsoft provide as well. First of all, there's PIX, which will be the focus of the rest of the presentation today, and that helps you debug and profile your D3D12 applications. We also have Warp, which I'll touch on later, which is our software rasterizer, as well as the debug layer and GBV for validation of what you're doing. But these are just the pieces of the puzzle that Microsoft provide. Within this ecosystem, there are tools provided by all the IHVs and also third-party tools such as RenderDoc. And so you really have to think about not just what we provide, but what the wider ecosystem provides as well. And so whatever GPU you're running on, there's always something that's going to let you be able to profile and debug what you're doing. So I'm going to split this into 3 parts. First of all, I'm going to talk about PIX. D3D12 is roughly 10 years old at this point, and so games are doing things that we didn't foresee them doing 10 years ago. As the last generation of consoles sort of fades into the distance, the Xbox Ones of the console generation, titles are beginning to do things that they weren't doing even 3 or 4 years ago. They're beginning to push the limits of both what the API was designed for and also the hardware. We've tried to keep pace with that by delivering new features in the D3D12 API incrementally. Features such as resource descriptor heap in shader model 6.6 really opened up the ability to go far more bindless in a much easier way than you could have with complex root signatures. But that flexibility comes at a cost. So tools such as PIX now have very little idea what you might be doing in your frame, what's stored in a given buffer, or how you intend to draw, what the contents of a texture mean. And so PIX has really had to try to keep up with developer interest in this increased flexibility. So I'm going to talk about some of the things the team's been doing to improve PIX customization in order to allow you to express what it is your engine or your title is doing. The first of those is a feature that we call custom visualizers. So what I'm talking about here is a feature that actually shipped in the December build of PIX last year and had been available in the Xbox version of PIX prior to that. So I have a screenshot here of a buffer. This buffer is a byte address buffer. It happens to be bound to an amplification shader in this case. It's got a name, it's called draw params, but PIX doesn't know what's in there. It could be floats, could be integers, 16-bit integers, bools, a custom structure. All PIX can do is just display some raw D words in hexadecimal and hope that you understand what those mean. So the custom visualizers feature can allow you to interpret your resources in 3 different ways. The first of those is the ability to reinterpret a buffer as a texture. So you've created a D3D buffer. It's a buffer, it has bytes in it, but you may know that that contains a texture of a given width and a given height. So PIX now allows you to custom visualize that buffer as if it were a texture. The second type of visualizer we have is the ability to reinterpret any arbitrary buffer as a mesh. And so gone are the days where you need a vertex buffer and a vertex shader in order to draw geometry. Your geometry might be stored in a byte address buffer or a structured buffer. It could be stored anywhere and in any format. It doesn't have to conform to a DXGI format. You can compress it into however many bits you're after. So here we have a custom visualizer that can take any arbitrary buffer, and through a shader that you provide us, we can visualize that to you as a mesh. And then the third type of visualizer is the ability to reinterpret a texture, still as a texture, but in a different way, with a different number of channels. It's not unusual these days to have a title use a 32-bit integer texture with a single channel and pack 17 bits of something in the top, and then another 5 bits of something else and 8 bits of something else. There's no 17, 8, 5 texture format, so you just pack all the bits into the 32, and then you're just left with this integer between 0 and 4 billion that PIX can just do very little with. So you can now write a custom visualizer that unpacks those bits and re-expresses them through color as a multi-channel texture. What do these custom visualizers look like? Well, there's a very simple one here. So you start by declaring the input resource that it is that you're visualizing. And so here we have a texture 2D declared as the selected texture at the top. And it's annotated with this special annotation, PIX X selected resource register. This just says this is the resource that we want to read from. The great power of custom visualizers is that you're not limited to reading just the resource that we're trying to visualize. You can read anything else that you would have had bound to that draw. And so if you're using resource descriptor heap, shader model 6.6, that may be access to literally any buffer or any texture in the resource descriptor heap. So if one texture provides the bounds to display another texture, then you can read those bounds from texture A and reinterpret texture B in that way. You can then include any other shaders that you want to include. These could be any of your includes in your entire engine. So if you've got shared code that is designed to pack and unpack this data, just include that directly in your visualizer. And then give the data back to PIX through this special intrinsic. It's just a UAV write with a special annotation so that we know which UAV buffer to go and read. And that's all there is to writing a custom visualizer. Step 3 is to tell PIX where your visualizers are located. So you can put these in a folder on your local drive, or if you have a shared drive that's mapped, a Z drive mapped to somewhere on the network that all your machines in your studio can access, then you can share those visualizers across the studio. Once PIX knows where the visualizers are, select the buffer or the texture that you're interested in visualizing, go to the visualization pane, and then at the bottom you should have all your custom written visualizers, and then you just have to pick one. So since this feature was delivered last year, as I say, slightly earlier than that on Xbox, these are some of the things that we've seen studios write. The dreaded nans that creep in a single pixel and then bloom their way all over the screen. You can write a nan visualizer or an inf visualizer to make those magenta much easier to find. We have people visualizing virtualized geometry, applying tone mapping and gamma correction, and visualizing just meshes, as I said. If they're stored or generated in a compute shader, written to a UAV buffer, maybe you just want to see that as a geometry as well. So we've had people doing that. So I told you about the 3 types of visualizers that we delivered last year, but conspicuously there was a missing one, and that was the ability to reinterpret a buffer as another buffer. Previously, we didn't think that you would want to do that, but of course, thinking about it logically, how some buffers may contain a level of indirection. They are an index into some other data structure, or maybe another buffer provides the scale in which to reinterpret this other buffer. We realized that we were going to need to do a buffer as buffer visualizer as well. So that will be coming in the April 2025 version of PIX. So that's all I had to say about custom visualizers. Anyone who's used PIX will know that there are these things called PIX events. That's the ability for you to scope in your code a given pass and say, this is the gbuffer pass, or this is the shadow map pass. As you call begin, you do the work, then you call end, and then PIX is then aware and can show you that this was the gbuffer pass or this was shadows. Last year at GDC, we talked about open sourcing what we call the WinPix event runtime. This is separate and distinct from open sourcing PIX, which is not something we've done yet. But we put the WinPix event runtime up on GitHub, and it's this library that provides those PIX events and PIX markers. So if you have an existing system that already has, maybe for other platforms, your own sort of event and your own event mechanism, and you just want to pull in the bits of the WinPix event runtime that allow you to emit your own PIX events, then you can just pull this off of GitHub and integrate those bits directly into the title. It's now, hopefully and gladly, very common for titles to use multiple threads for their command list recording. Maybe when D3D12 was built, we envisioned someone creating a thread, creating a command list, and then recording that command list to completion. But what we see increasingly some engines doing is starting the recording of a command list on one thread, then handing that command list off to another thread in order to record some more commands and maybe then close the command list. And so if you put PIX events, you put a begin event basically on one thread, hand that command list off to another thread, and then that other thread is the one that calls end PIX event. And so from PIX's perspective, it sees one thread doing lots of begins and no ends, and it sees another thread doing lots of ends and no begins. And so when we try to visualize that hierarchy of PIX events, it looks recursive from PIX's perspective because we have these unmatched pairs. And so what you end up with is this situation on the right-hand side where you start a PIX event and it just recurses and recurses and recurses, and you just get into a very broken situation. And so we've addressed that with the with the April version of the WinPix event runtime. There's no additional changes required on your behalf. You simply just have to update to the April version of PIX, and this broken recursive hierarchy will look as you expected. So that's 2 ways in which PIX is increasingly able to sort of be customized by you, the developer. But there is a third one that we're announcing today, and that's the PIX API. It is our vision, and this will be delivered over time, for there to be a PIX API upon which PIX is built that allows you programmatic access to anything that a PIX capture can currently display to you in the UI today. So this PIX API should look familiar to anyone who's used D3D12. It's just a nanocom C++ API. And since we imagine this is going to be used in tooling quite a bit, we've projected that API to C# and Python as well. It'll support CPU captures and GPU captures. And if anyone has used the PIX tool executable before, you can think of this as a sort of spiritual and more feature-filled successor to that. So PIX tool was simply an executable that allowed you to, you provided a PIX capture, and you could interrogate certain information about the PIX capture, like the timings and things like that. But the PIX API, because PIX the UI will be built on top of it, will be able to provide you anything that you want to know about a PIX capture. But previously would have required you to open up PIX, open up the capture, hit analysis, and then go through copying and pasting it into Excel and saving out buffers. Whatever it was you had to do to get that information out should now be purely programmable. So we see three main use cases for using the PIX API, and the first would be around performance regression testing. It's not unusual today to have developers have their build machines build the game overnight, and then not just build it, but actually run it. You know, drive the car around the world, run around the world, go in and out of every level, and capture performance information as you go. And so you can now take PIX captures programmatically. You can do that part today. You can take the PIX captures programmatically, but you would never have had a way until now to be able to interrogate what that PIX capture is actually going to tell you. So you can have the build machine take a PIX capture, and then through using the PIX API, load that capture up, and analyze it, and get the performance data out of it. A second obvious use case is in visual regression testing. Again, the build machine could be running in and out of every level, taking a PIX capture at a certain point, and then saying, is this image the same as it was yesterday? Does it have the object on screen that it should have on screen? And so you can start identifying visual regressions in an automatic way through the PIX API. And the third somewhat related use case is just simply batch processing of these PIX captures. You might have a library of 10, 20, 1,000, 10,000 PIX captures, but today you would need a human in the loop to go and open up PIX, open up every single one of these PIX captures, play them one at a time, capture all the information. But so simply having an API will speed up the batch processing of PIX captures. As for what that looks like, it's a very simple API, and as I say, it's available in both C++, C#, and Python. And so I won't read through the code here, but it's as simple as simply opening the capture and just interrogating information out of it. It's not going to be foreign to anyone who's used to D3D12. This PIX API will initially be available only in a private preview. So if this is interesting to you and you want to try out the PIX API before it's fully available in a retail version of PIX, hit the Ask WinPix alias up, and we can get you hooked up with that preview in April. So that's all I had to say about PIX customization, but that's not all the PIX team have been working on. And so Claire's talked to you already about the new features we're adding to DXR 1.2, plus cooperative vectors. And we're glad to say we have a rule at Microsoft that if we ship a new feature, then PIX needs to be able to support it. There's no point adding a new DXR feature, hitting capture in PIX, and it says, I don't know what OMMs are, and then failing. So PIX will come with day one support for OMMs, SCR, and cooperative vectors. Last year, we talked about work graphs quite extensively, and true to our word, we shipped work graph support in PIX at that time. But the definition of support for work graphs was really limited to being able to capturing work graphs, analyzing them, and displaying you a little bit of information about the work graph. At that time, we did not have work graph shader debugging. I'm glad to say that that support is now in place, and so you can debug your work graph shaders in the same way that you would a vertex shader, compute shader, pixel shader. We've also heard a lot of feedback from developers about the general UX experience of using PIX. And so this is how PIX looked in the current latest build shipped in January. Starting in the April 2025 version of PIX, we've revamped the UX. We've heard a lot that some features were just simply not discoverable. They were there, but you didn't know what menu they were behind, or there were too many clicks, or maybe they weren't in the default layout. So the team has really been focused on the UX of PIX and trying to get that information to you through the fewest number of menus, the fewest number of clicks, making it much more discoverable, the features that PIX has. And so PIX is trying to follow some more modern design practices, less menus that open out over the full screen, more flat menus, more buttons, just things that are just much more intuitive to use. And hopefully through this you'll be able to discover those features that PIX has maybe already had for years, but you simply didn't know existed. One of those features that was very hard to discover was the layout editor. I know I've been on site with studios who use PIX, and I've asked them casually, oh, just add me a new output window there, and they've looked at me like, what do you mean add a new output window? Like PIX, this is how PIX looks. And I was like, just click that button in the top right-hand corner. And then there was an entire layout editor there. The problem was it didn't work like any layout editor you've ever used before. So even if you did find it, it was pretty difficult to lay out the UI in the way that you wanted. And so the team went back and looked at other Microsoft products, ones that you're probably all familiar with, like Visual Studio, and we've adopted that design practice. So you can now just drag and dock, undock, move to other monitors, dock bottom, dock left, whatever it is you think you can do in Visual Studio with the code windows and Solution Explorer. This will feel very at home for you. Some of the other improvements that the team have made are around simply just capture reliability. The team are always trying to get to, of course, 100% capture and analysis rates. But some features have been added recently to both to PIX actually and the D3D API to get that 99.9% much closer to 100. DXCPL.exe is a standalone executable today that's called the DirectX control panel, and it offers options for you to force features on, like GBV, the debug layer, force features off. And so that UI is now integrated directly into PIX rather than requiring you to open a separate executable. We've shipped some new visualizers for render targets. So those pesky helper lanes, if you don't know how many you've got, then there's a new quad utilization visualizer for that. And also for the variable rate shading, the VRS shading image. Ray tracing has had some love as well, so we continue to build on the acceleration structure viewer inside PIX, give you more information about the TLAS and BLAS hierarchy you've got. And all of this is, again, coming in the April 2025 version of PIX. Second, I'd like to touch on Warp. So for those of you who are not aware, Warp stands for the Windows Advanced Rasterization Platform. And you can think of this as simply as a CPU-based GPU. So either your machine might not have a GPU in it, in which case the Windows desktop uses Warp, or you might come across what you believe to be a IHV shader compiler bug or some issue in their driver, and you just want a sanity check. You know, is this my issue, or is this going to reproduce on other GPUs? And so Warp is great for that. You can just toggle on Warp and have a CPU-based rasterizer. It's not very fast, but it'll at least get you into your game and give you some indication of whether that bug you're seeing is the NVIDIA driver's fault, AMD driver's fault, or maybe it's common to both and Warp, in which case it's probably your issue. So Warp is undocked from the Windows release schedule. So you can, in the same place that you would get the AgilitySDK or the WinPix event runtime, you can just download the latest version of Warp from NuGet.org. Historically, we'd underinvested a little bit in Warp, and so it wasn't able to support games that were using ray tracing or mesh shaders or work graphs, but we've reinvested in that, and all those features are now supported through Warp. Warp is now a feature level 12.2 GPU, in quotes. And the performance has been worked on as well. It's never, of course, going to match a physical discrete GPU, but we want it to be at least fast enough for you to be able to get into the game, maybe at a lower resolution than it would usually run at, and at least be able to interact and move around. So performance is a constant focus for that team. And just like with PIX, we'll support OMMs and SER and cooperative vectors when those features are shipped. Lastly, I'd just like to touch on validation. So the debug layer can be enabled, and that is a CPU timeline-based validation. So that's basically, one part of it is just checking your API arguments. If you've asked D3D for a texture that's 1 million pixels wide, well, that's an error. If you've asked for a buffer with 10 MIPS, that's an error. Buffers can't have MIPS. So that's why the debugs layer is there, to catch those things on the CPU timeline, things that it can figure out before the GPUs even started executing the work. And likewise, the debug layer will, of course, have support for OMMs, SER, and cooperative vectors. GBV is the GPU-based or GPU timeline validation. So this is checking things that the CPU can't know at command list record time. Things like whether your shaders accessed an invalid descriptor or a descriptor of the wrong type. This was another area where we'd underinvested a little bit, and GBV is now catching up with those features that we've been shipping in the last few years. So shader model 6.6 resource descriptor heap is now supported, as are mesh shaders, but not yet ray tracing. We're still working on that one. GPV does involve recompilation of your shaders to inject that extra validation code, so it comes at a high performance cost. But again, we're trying to work on that and get you at least into interactive frame rate territory so you can navigate around the game. And if you haven't used these before, they're just one function call to enable each one. Just call these before device creation. So in summary, Claire has talked to you about the DirectX AgilitySDK preview that's coming in April with OMM, SCR, and cooperative vector support. Warp will support all those features on day one. PIX will support all those features on day one, and then come with this refreshed UI or UX experience with the new layout editor and improvements to the custom visualizers and more. Just a few plugs for the various places in which you can reach us. So we have the DirectX and PIX blog, which is where we announce features coming out first. So if you keep an eye on those blogs, that's where you'll hear about the latest things. We also have the DirectX specs GitHub page. That's any feature that's been added in D3D12. There's a spec for it, and sometimes it's a little bit more useful than the MSDN documentation for really getting into the nitty-gritty of what a certain feature is supposed to do in a certain case. We also have a DirectX Discord server. This is not community run. This is a Microsoft-owned Discord server. It's got 20 or 30 Microsoft employees in it across the D3D team, the PIX team, HLSL team, ATG. So if you have a sort of non-NDA sensitive question that you think the community might benefit from hearing the answer to, we're all in there, and you'll usually get a response within 24 hours. If you want to reach out to the PIX team directly, maybe it's a more sensitive issue, you want to provide a PIX capture of your game that you obviously don't want to share publicly, we have the Ask WinPix alias as well, and that gets directly to the PIX team, and again, I would expect a response within 24 hours or on a business day. So with that, I think we've probably got maybe 5 minutes for questions, but as Claire mentioned, we'll be at the alcove after this talk, and then we'll also be in the South Hall, the Xbox Lobby Lounge in the South Hall between 4 and 5 p.m. We can take any further questions you have there, but for now, I think we've got about 5 minutes. So if you have any questions, just step up to the mic and we'll see what we can do.
I have a question about the schedule of the title alignment. I think the title alignment is a preview feature now.
Yes.
Do you have a plan when the title alignment is released officially?
Yeah, thanks. About title alignment in retail, tentatively, we're going to say like the general flow we have is about 6 to 8 months from when we release a feature in preview to retail. So I would say that's the timeline that this will be.
Okay, thank you.
Yeah.
Hello, I have a question about the opacity micromaps. If I understand correctly, it subdivides the geometry and stores additional geometry information. So now at this point we have a opacity information as a texture in memory and also as a geometry data in memory. Wouldn't it be just easier to ditch the texture and just model out the leaves in geometry at the first place and don't use opacity micromaps?
Yeah, so I would say the opacity information is stored in a different format from your geometry, and that's for a good reason. You can find more information, I think, when we publish the spec, but there's kind of like a bird order type format that lends itself to a really efficient traversal, and it's different from the geometry format, and you get benefits from it being different. So I'd say that's, a description of how it works. And then, yeah, when we have the spec, I think you'll be able to read more about how the format works.
Okay, thank you.
Oh, yeah. Yeah, a quick reminder too, when you came in the door, I think you were given a survey. if it's not too much trouble, if you can fill out that survey so that we can all benefit from your feedback. No? Okay, thanks everyone.